Now we're going to solve Cambridge IGCSE Physics, October-November 2024, paper 4.1. So number 1, a spring is suspended from a clamp. Figure 1.1 shows a pointer attached to the lower end of the spring. A student suspends loads of different weights from the spring and records the readings on the meter ruler. Figure 1.2 is a reading weight graph that the student obtains. A1. Using figure 1.2, determine the reading on the meter ruler. 1. No weight is attached to the spring. So there's no weight. That means it's 0. It's just the intercept. So that would be like either 42 and the 43. 43 centimeters. And a weight of 5.6 newtons is attached to the spring. 5.6 will be around here. This is 5.6, and you go up and you see this. That is around 63. That is 63 centimeters. So calculate the extension of the spring when the weight attached is 5.6 newtons. Extension is just subtracting from the original length, so that'll be 20 centimeters. Using the values found in A, calculate the spring constant of the spring. So the spring constant, we have this equation, K is equal to force applied divided by extension. So force applied is 5.6, and then extension was 20 centimeters. So that would be 0.28 Newton by centimeter. C. An object of mass 0.5 kilograms is attached to the spring. Calculate the weight of the object. So weight is equal to mass and the gravitational free strength. And so that would be like 0.5 into 9.8. And that is 4.9 newtons. So 2, the object is pulled downwards until the tension in the spring is 6.5 newtons. The object is released. Calculate the acceleration of the object immediately after it is released. So to get the acceleration, we know like the force and then mass as well. So this equation could come into mind. But we have to know that the force F represents the resultant net force. So here we've got like two forces acting, like the weight of the object acting downwards and the tension of the spring, it will be like holding. So that will be acting upwards. So they kind of like oppose each other in direction. So you have to like subtract to get the net force, which means 6.5 subtracted by 4.9, and that will be equal to mass is 0.5 into acceleration. So acceleration would be equal to 1.6 divided by 0.5, which is 3.2. So we get 3.2 meter per second square. So number 2, a drag car is a racing car that is powered by a rocket engine. A drag car accelerates uniformly from rest until it reaches the finishing line. The engine is then switched off and parachute opens. The car decelerates until it stops. Figure 2.1 shows a drag car decelerating after a race. So a drag car has a mass of 1400 kilograms. So figure 2.2 is a speed time graph of the car during a race on a straight horizontal track. So calculate the maximum momentum of the car during the race. So let's just write the equation. Max momentum is equal to mass into velocity. And they also give us like the maximum speed. So to get maximum momentum, we use maximum speed, and then we also have the mass as well. So mass was 1400, and the velocity is 130. To multiply that, that is 14, 14 to 13, 182 AG meter per second. So we convert that to two significant figures and write in standard form. So 1.8 into 10 power 5 AG meter per second. And to state the feature of figure 2.2 that represents the distance traveled by car. So this is a speed time graph. So if you want the distance, you get the area under the graph. So yeah, you just write area under the graph is represents the distance. So determine the distance traveled by the car in the first 6.5 seconds. 6.5, I think this will be 6.5, but let me make sure. So 12, midpoint is 6, and then this is, they're like 5 little squares, which means 2 divided by 5, 0.4. So this is 6.4. Yeah, this is 6.5. So this is just a triangle, and the height is something like probably 130, yeah, 130, the midpoint. So yeah, area is going to be equal to 1/2 into the base. Base was 6.5 obviously, and then height would be 130. So we get something like 0.5 into 6.5 into, and 30 is 422.5. Yeah, so the distance 420 meters. B. The parachute opens at 6.5 seconds and the car decelerates. Describe how figure 2.2 shows that after 6.5 seconds, 1, the car decelerates. So if the car decelerates, then the gradient, right? You get the acceleration in speed time graph by looking at the gradient. So the gradient is negative. So we can just write negative gradient. And the deceleration is not constant, and that is because gradient is not constant. Gradient is not constant, and how do you know it is not constant? It is because the graph is a curve. So C, describe the energy transfer that takes place as the car slows down. So initially it has kinetic energy obviously because it is moving, right? And as it slows down, there is like some kind of friction. You need to overcome that to slow down, and that will be converted to thermal energy. 3A, define the moment of a force and describe the effect that it measures. So for definition, we can just write the equation, right? So force into perpendicular distance from pivot. And what does it measure? Moment is, it just measures the turning effect of a force. So B, a large rectangular block of stone has a square base of side 3.4 meters. Figure 3.1 shows the block at rest on the horizontal surface. The block is of uniform density and the center of gravity as its center. Explain what is meant by center of gravity. So the center of gravity of an object is like here at the point on which the gravity acts, and the gravity acts because there's weight. So in simple terms, we can write something like it is the point at which weight of an object acts. So 2, the weight of the block is 1.3 into 10 power 7 newtons. Calculate the moment of the weight of the block about the corner x. So this here is a corner x. So we can like do something about weight moment. So we can say this is like the period, right? Because it is about x. So where is the force? The force is right here, right? Gravity is acting on here. And we can think about equation. We know the force. Force is the weight, and then distance. Center of gravity is like it says uniform density in it at its center. So because it's center, so it'll be like exactly midway point of the width. So we get both the distance and force. So we can multiply force, and then the distance would be like 3.4 divided by 2. So 1.7 into 1.3 would be 2.21 into 10 power 7. So we can take like 2.2 into 10 power 7 Newton meter. See, the block shown in figure 3.1 is in equilibrium. State 2 different conditions that apply when an object is in equilibrium. In equilibrium, that means there is no movement at all. It's just still. And that will be because there is no acceleration, no velocity, which means there is no net force. And there will be no moment, no net moment as well, because it's not like rotating or anything like that. So for A, describe an experiment to determine the specific heat capacity of aluminum. You may draw a diagram, including your answer, the measurements made, and equations needed. So firstly, because we're looking for specific heat capacity, obviously we need the equation of that. So C is equal to delta E divided by m delta T. So when you think about it, we can find energy. But how, right? So firstly, we will think that we have this aluminum block. And this aluminum block will be heated by electrical heater. And that will be connected to power. So if we know the power rate then and we measure the time, then we can calculate for energy given. So E is equal to power into time. So we get the total energy given by this equation, and then we can substitute that into here and get the specific heat capacity. So these two are the equations that we need. So, and then we have to describe the measurements as well. So the measurements needed will obviously be the time taken that you give that power to, and then the mass of the aluminum block, because you can see that in the equation, right? So those are the quantities that you need to know. And then initial temperature, so you obviously need a thermometer. Initial temperature, and then final temperature. So you have to describe the experiment. So this is just some ideas of what to include in the description. So here it says you may draw a diagram. Personally, I'm not particularly good at that, and so I'll just skip it. Right, but to give you an idea, this is an aluminum block, and this will be some kind of heater connected to power. And then you will have a timer here, and then some thermometers, and you will get to measure the temperature. So firstly, we will have measuring the mass. Measure the mass of the aluminum block and heat it with an electrical heater connected to a power source. Then timer, we can start the timer, and before that we have to measure the initial temperature as well. So we will measure the initial temperature firstly. Measure the initial temperature of the aluminum block. Then measure the mass. Of it. Then start the timer. And after an appropriate time, like for example 3 to 4 minutes, appropriate duration, stop the timer and measure the final temperature. Then you will get the time. You already know the power rate, and then you get the energy. And you can just write the equations needed here, like this. So yeah. B. An aluminum dish is initially at room temperature. Boiling water is poured into the aluminum dish as shown in figure 4.1. 1. Explain why, after a short time, the dish and the water are the same temperature. So this is something about heat transfer, right? So heat is always transferring from like high energy to low energy to balance out, right? So we can write this is because this is due to the heat transfer from high temperature to low temperature by conduction, because they are touching each other. And it asks for like after a short time, so you have to know that the process is fast, and this is because aluminum is a good conductor of heat, and the temperature of water decreases while the temperature of aluminum increases. So you show this transfer. So number 2, explain in terms of its particles why the aluminum expands as the boiling water is poured into the dish. So things like materials, they do expand after receiving more energy. So this is because of this thermal energy, right? So as thermal energy is transferred, transferred to aluminum particles, they increase in kinetic energy. So they move faster. As they move faster, they expand. Not they expand actually. They move away from each other. They move away, like farther from each other. For aluminum to like expand. Number 3. The water in the dish evaporates. Explain in terms of water molecules what is meant by evaporation. So evaporation happens right when those water molecules they get enough energy to leave the surface. So it's just that. So water molecules with enough energy escape. Escape, we can say something like move out, maybe. Escape is a better word. Escape from the surface of the water. Number 5. A loudspeaker produces a sound wave in air. The distance between the center of a compression and the center of neighboring refraction is 0.1 meter. So calculate the wavelength of the sound wave. So wavelength is like the distance between two adjacent compressions or rarefactions. So if it's like if the distance, the 0.1 is between a compression and a rarefaction, that means you only get in half of the wavelength. So you have to multiply with 2. So you get 0.2 for 2 significance, 0.20 meters. State a typical value of the speed of sound in air. So this is something that we have to remember, right? So that's 340 meters per second. And C1, calculate the frequency of the sound from the loudspeaker. So we have this wave equation, right? V is equal to F lambda, F wavelength. So you know the velocity, and then we want the frequency, we know the wavelength. So we do the math. F will be equal to 340 divided by 0.2, and then we get 1700 hertz. So to explain whether the sound from the loudspeaker is audible to a human with normal hearing. So for the human hearing range, that is between 20 hertz and 20,000 hertz, and 1700 will fall between them. So yes, the sound is audible because the frequency is within the human hearing range. So D, another loudspeaker produces a sound of wavelength 0.4 meters. Sound from a loudspeaker reaches a sound absorbing surface with a gap of width 0.8 meters at its center. So figure 5.1 shows the arrangement. Explain whether it is possible to detect sound from the loudspeaker at either point J or at point K. So these are 2 points, and this is essentially testing diffraction knowledge. So this is 0.8, which means the gap is larger than the wavelength. It's like twice really large. So that means that the diffraction will only happens a little bit, like something like this. So whether it is possible to detect from J, well, it will not diffract that much, so it is like very less likely that it will reach this J, so there will be like little to no sound heard. But for K, it is closer, right, because it's 0.8 closer, so it can be heard somewhat in K. So we can explain that for point J, right, there will be little sound is heard at point J because gap size is much larger than the wavelength. So diffraction effect will be small. But for K, sound can be heard at point K because it is close to the waves coming from the gap, like between waves. Coming from a loudspeaker, so this should be enough. So number 6, a potential divider is made by connecting a light-dependent resistor LDR and a thermistor in series. Figure 6.1 shows the potential divider, a voltmeter, and a direct current power supply connected to a circuit. So the voltmeter measures the potential difference across the LDR. Define the potential difference. So this is asking for the definition. So potential difference is essentially just work done per unit charge. So, work done per unit charge around work done per unit charge through a single component. So number B, the electromotive force of the supply is E. Describe how the potential difference across the thermistor can be determined using the reading on the voltmeter. So it asks for like thermistor, and we want the PD across thermistor, and this is E. So you have to know that in series series circuits, the EMF, it will be divided between the components. So we can just say like E subtracted by reading on voltmeter. So C1, the resistance of the LDR decreases and the resistance of the thermistor increases. State what has happened to the light intensity incident on the LDR and the temperature of the thermistor. So if the resistance decreases, like both of them, like they're like inversely related to each other. So if resistance decreases for LDR, then the light intensity will be increased, and then for temperature it will be decreased. Explain what happens to the reading on the voltmeter. So because the voltmeter is connected to LDR and the resistance decreases, the voltage, the reading, it will be decreased. So this is because first of all, we have this connection between voltage and resistance, right? So they are directly proportional to each other. So that's one thing. And then the EMF, it's constant. So just because the resistance, you don't need much voltage anymore, the EMF provided won't be less. So that's the second point. So we can write that the reading decreases, and it is because the resistance and potential difference is directly proportional to each other, and EMF provided is constant. So for the first point that we mentioned, we can also write something with the equation instead of this thing. So we can write that R1 divided by R2 is equal to V1 divided by V2. Number 7. A solid bar is inside a copper solenoid. Figure 7.1 shows that the copper solenoid is connected in series with a battery and a variable resistor. The device shown in figure 7.1 is an electromagnet. It suggests a suitable material for the bar. So this is an electromagnet, so we use soft ion in these conditions. B. The right-handed end of the bar is south pole. Figure 7.2 shows the bar viewed from above. And on figure 7.2, draw at least 6 field lines to show the pattern and the direction of magnetic field surrounding the bar. So we can note this is north pole. We don't have to write it, but this is just showing. So 6 field lines. So you have to put the direction as well, the arrows. It is going from north to south like this, and then we can have 2 straight ones. Two and then 3. Number 2, the resistance of the variable resistor increases. Explain what happens to the magnetic field surrounding the bar and state how the pattern of field lines that represent the field changes. So if resistance increases, the current will decrease because they're inversely proportional to each other. So if the current decreases, then the magnetic field, induced magnetic field strength, it will also decrease. And for the pattern, it shows if the strength is decreased, then the field lines, they will be farther from each other. So that's how you show the low strength of magnetic field. So we can write the current in the coil decreases as it is. It's not, I wouldn't say it is inversely proportional. It's inversely related to the resistance. And therefore, thus, the magnetic field strength decreases. The field lines will be farther apart with each other. C. A square coil of many turns is placed close to the bar. Figure 7.3 shows the plane of the square coil parallel to the flat circular surface at the right-hand end of the bar. The resistance of the variable resistor is alternately increased and decreased. Explain what happens in the wires of the square coil. So because the resistance is happening like that, so there will be change in current. So the current will be changing through the wire, and this causes apparently the change in magnetic field. So if there is change in current, there will be change in magnetic field, and then because of this change in magnetic field, the electromotive force will be induced between between the terminals of the wire. So we can write that due to change in resistance, the current is changing through the solenoid. So this causes changing magnetic field, So electromotive force, we can just write EMF is induced in the wires of the coil between the terminals. Number 8. The nuclide notation for the radioactive isotope carbon-14 is 14 C6. Using the symbols shown on figure 8.1, draw a diagram to show the number of electrons, neutrons, and protons in the neutral atom of carbon-14 and how they are arranged. So you have this nucleus in here, but like you can draw it like that. So we have to show proton and neutron separately as well. And this is the number of electrons or the number of protons. So we can draw 6 of them here. 2, 3, 4, 5, 6. So all these 6 of them, they have to be like colored. I should be more careful with this. So I'll just draw 14 of them because neutrons are also circles. So I can just color 6 of them. So like you have to know, like protons, they won't be like really close to each other. They have to be kind of like separated, because they repel. So you can choose like places. Okay, and then we can draw the electron shells. This feels like chemistry now. So in here you only have like 2 electrons, and then only here you get 1, 2, 3, 4. So B, describe how the composition of a neutron atom of carbon-14 is different from the composition of a neutron atom of nitrogen-14. So the number of electrons and protons will be different, right? So, and then the neutron number will also be different. So we can write something like, okay, so how carbon atom is different. So we have to write from carbon atom perspective. So carbon-14 atom has 1 fewer proton, we can write electron, and 1 more neutron. Then nitrogen-14 atom. C, carbon-14 decays by beta emission. 1, state the name of a particle that is identical to a beta particle. So that is a negative charged particle, so that would be, you can say, electron. Describe the change that takes place in carbon-14 as a beta particle is emitted. So as beta particle is emitted from the nucleus, like a neutron, it changes from neutron to a proton and then an electron. And 1 electron will be released, and there will be 1 more proton. So you can say that the overall charge, it becomes like positive in some sense. So we can just write the change. A neutron in the nucleus is changed into a proton and an electron. So the half-life of carbon-14 is 5,700 years. A very old object is made of wood. It contains 1.2 into 10 power 11 atoms of carbon-14. When it was manufactured, it contained 9.6 into 10 power 11 atoms of carbon-14. So determine the time that has passed since it was manufactured. So that means that to calculate the time, you need to know the number of half-lives. So to calculate the number of half-lives, we can use these two, right? So we can know that after so 9.6 divided by 2, 4.8, 2.4, 1.2. So after 4 half-lives, 1 half-life, 2 half-life, 3 half-lives. So after 3 half-lives, you will get this amount of atoms left. So you can say that it has 3 half-lives. And for the time, you can just multiply 3 into 5,700, which is 70,100. So it's 17,000 years. Number 9. The Milky Way is a galaxy in which the solar system is located. State what a galaxy is. So a galaxy is just a very large collection of stars. So we can write probably maybe a massive collection of, you can even write billions of stars. So the Milky Way has a diameter that is approximately equal to 100,000 light years. Determine this distance in kilometers. So I need to know that 1 light year is 9.5. 1 light year is equal to 9.5 into 10 power 12 kilometers. And if it is 5 more zeros, then we can just add 9.5 into 10 power 17 kilometers. So C. Astronomers determine the speed and distance from the Earth of a far galaxy that is moving away from the Earth. 1. State one observation that allows the speed at which a galaxy is moving away to be determined. So this is about redshift, right? If it's moving away, the observed wavelength will increase. That's just, talking about redshift. So you can also say the increase in wavelength, increased in observed wavelength, or just the amount of redshift. So I just write amount of redshift. To state one different observation that is used to determine the distance to a far galaxy. So there's another quantity that you can use to know the distance of a very far galaxy, and that is called the brightness of a supernova happening in the galaxy. So supernova is one of the brightest things in the universe, and if it happens, we can observe very, very far away from the space. So you can use that as the standard candle to determine the distance. So you can just write brightness of a supernova. 3. State how the speeds of galaxies and their distances from the Earth are related. So if a galaxy is moving away from the Earth at a faster speed, that means they're also farther away from the speed. So I'm just saying that those speeds and distance, they are directly proportional to each other. So we can say that speeds of moving away is directly proportional to the distances from the earth. For the best estimate for the Hubble constant, h0 is 2.2 into 10 power minus 18 per second. Use this value to calculate an estimate for the age of the universe. So we have this equation, right? The age of the universe is 1 by h0. And we can put that in calculator. 1 divided by 2.2 into 10 power minus 18. That is 4.545, something like that, into 10 power 17. So to take two significant figures, we can just write 4.5 to 10 power 17 seconds. So this is the end of the paper. Good luck with your studies.